So today we will solve a problem of cantilever sheet pile in cohesive soil. In the previous lecture we have solved a problem which was in cohesionless soil. Today we will solve a cantilever sheet pile problem in cohesive soil. Cohesive soil, that means phi equals to 0 and there will be apparent cohesion in the soil. So design is almost the same for cohesive and cohesionless soil. We will solve the problem in conventional method likewise, but in cohesive soil, two cases of cantilevered walls in cohesive soils are of interest. One, sheet pile walls entirely in clay, and two, walls driven in clay and backfilled with sand. In these both cases, different lateral earth pressures develop for each cases. Now, for case 1, when wall is entirely dipped in cohesive soil, design of sheet piling in cohesive soil is complicated by the fact that the strength of clay changes with time, unlike the cohesionless soil, and the lateral earth pressure also changes with time. The depth of penetration and the size of piling must satisfy the pressure conditions that exist immediately after installation and after the long-term conditions. The strength of the clay has changed. So the problem we will solve today in cohesive soil by conventional method will be basically divided in two parts. At first, we will solve the problem for initial strength condition, where only cohesion of the soil is present, and the second part we will solve the problem for final strength condition, where the properties of the clay, especially strength properties of the clay, has changed. So immediately after the sheet piling is installed, earth pressure may be calculated on the assumption that undrained strength of the clay prevails. That is, it is assumed that the clay derives all its strength from cohesion and no strength from internal friction. So that means for initial strength condition, we will take only the cohesion of the soil that appears in the soil. So there will be cohesion C, but no internal angle of friction will be developed for the initial strength condition. So phi will be equals to 0. And then after some times, when the drainage of the soil will occur, then there will develop angle of internal friction. So the final strength condition, there will be no cohesion, so cohesion C will be equals to 0 and there will be angle of internal friction phi. So for initial strength and for both final strength condition, we will determine the value of embedded length of sheet pile and we will see which one governs. Okay, now let's start the problem. This is the problem we will be solving today. As we all can see, this is the depth of embedment length. Let's take it as D, capital D. We will have to find the depth of embedment length. As we all can see, here is also just like the other problem, two stratification of soil is observed. At first layer for from this first 13 feet, the soil properties is given, which is gamma equals to 110 PCF, C equals to 0, phi equals to 27 degree. And the second layer of the soil properties is given likewise, gamma 2 equals to 115 PCF, C2 equals to 800 PSF, and phi equals to 0, as I have told you earlier. So the second layer we can see, which is purely cohesive soil. So as I have discussed already, that two types of cases in cantilever walls in cohesive soils are of interest. The second wall, as the second case I have already discussed, wall driven in clay and backfilled with sand. So we are solving the problem of the second case, which is this cantilever sheet pile is driven in clay soil, which is this, but backfilled with sand layer. The backfill of which can see the properties C equals to 0 and phi equals to 27 degree. That means purely granular soil. As a backfill, the soil used is purely cohesionless soil. Okay. Now, just likewise before, as we have already solved another problem, we will determine the same things: vertical overburden pressure sigma 1, earth pressure P1, horizontal force H1, and we will take for the static equilibrium summation of H equals to 0 and moment at point O will be equals to 0. Okay. Now, as I have discussed earlier, for cohesive soil embedment length of sheet pile, we will solve this in two segments. At first, we will solve this for initial strength, and secondly, we will solve the problem for final strength. So, now we will solve it for initial strength condition. So for I would like to recap again. Now for initial strength condition, C will be there, but no internal angle will be developed. Okay, now let's start. Again, we will, at first what we will do, we will develop the earth pressure diagram. Okay. Let's draw the problem again. So we will determine the value. This is the granular soil, this layer is granular, and this is cohesive soil. So again we will determine the overburden pressure at this level, which is sigma V1, overburden pressure at this level, which is sigma V2. Okay, now overburden pressure sigma V1 equals to gamma H. So what was the gamma? 110 into h equals to 3. Okay, PSF. Now we will have to determine the earth pressure P1. Okay, Ka gamma h minus 2c root over Ka. So here, let's go back to the problem. Here we can see c equals to 0 and phi equals to 27 degree. So let's find out the value of Ka, which is 1 minus sine 27 degree divided by 1 plus sine 27 degree. You can use this equation also, it's up to you. So that sums up Ka equals to 0.38. Okay, now putting the value of Ka in this equation, we get Ka is equals to 0.38 into 110 into 3. Since c equals to 0, this term is also 0. So that makes P1 125.4 PSF. 125.4 PSF. Okay, now let's find out the value of P2. I'm not going to elaborate on this because I have already discussed elaborately on the previous lecture. So let's find out the value of P2. 110 into 3 into 0.38 plus 110 minus 62.5 into 10 into 0.38, which makes it 305.9 PSF. So P2 is equals to, this one is P2 is equals to 305.9 PSF. Now, since from this point soil stratification occurs, so here the slope of earth pressure diagram will also occur. So let's take the earth pressure at point 2 as P3. So for P3, what we will have to do, for the previous problem we have solved earlier, here the both layer was granular soil, this layer and this layer, but in this problem, as we all can see, the first layer is granular soil and the second layer is cohesive soil. So for cohesive soil, what is the earth pressure by Coulomb's theory? What is the equation of solving earth pressure? With Ka, sorry, Pa, which is active earth pressure or active thrust, is Ka gamma h minus 2c root over Ka, and passive thrust is Kp gamma h plus 2c root over Kp. For the previous problem, since in both layers c was 0, so only vertical overburden pressure factor was considered for the earth pressure diagram. But in these cases, the second layer cohesion is there, so this term will also be added since determining the value of earth pressure. So we will have to determine the value of earth pressure at this level. We have determined up to this point. We will have to determine the value of this point. Let's take this point as 3 for the convenience. Okay, then P3 will be, sorry, so P3 will be determined. So what will be P3? Active thrust of this point minus passive thrust. Okay, now we will write the equation of P3. Active thrust minus passive thrust. Okay, active thrust will be 100 into 3 plus 110 minus 62.5, which is the unit weight of water, into 10 into Ka2 minus 2 into C into over Ka2 minus passive thrust Kp2 into gamma h, since h equals to 0, plus 2 into C into root over Kp2. Okay, now for this layer, since this is the initial point of the second layer, we will have to use the strength parameters value, which is cohesion C and angle of internal friction value phi of second layer. So C equals to 800 psf, phi equals to 0. Since phi equals to 0, that means Ka2 will be 1. So 1. So Kp2 will be 1 by Ka2. It will be also 1. So now the value of P3 will be minus 2395 psf. So why is it minus? Since we are taking it, this side is positive compression, which means active thrust. So as I have discussed, that this active thrust tries to deflect the sheet pile in this way, and passive thrust from this region again neutralize it and move it back towards its initial point. So minus 2395 is actually the passive thrust. 23 P3 equals 2395. Now we got our earth pressure diagram up to this point. Okay. Now, just like the previous problems, we will have to determine the values of P4 and next P5. P4 will be 100 into 3 plus 110 minus 62.5 into 10 plus 115 minus 62.5 into D into KP2 plus 2 into C into root over KP2. Okay. P4 is equals to this is the passive thrust. Okay, will be passive thrust minus active thrust. So which will be 115 minus 62.5 into D into root over into Ka2, which is 1 minus 2 into 800 into root over Ka2, which sums up 405 PSF. So this is P4. Okay, P4 is equals to 4005 PSF. Okay, now there is a very clear distinction between the previous problem and this problem, which is that, as you can see, this earth pressure in this earth pressure diagram for cohesive soil, this part is constant. Constant means the slope is vertical, there is no increasing or decreasing pattern in slope. Okay, now let's, because as we can see in determining the value of P3, we have determined active thrust minus passive thrust of this region when the sheet pile enters in the second layer of the soil stratifications. Passive thrust from this region and active thrust of this region makes the cantilever sheet pile in this position. So we have determined the value of we have determined the value of P3 2395 PSF 2395 PSF, and this value will be unchanged up to this level. So why does it happen? Because you can see it in this equation of P3. You can see this, the active thrust minus passive thrust. For passive thrust, only C is there. Gamma H portion is equals to 0 for the initial point. You can determine the value. Let's take a point H, which is H equals to 2 feet. You can determine the value of earth pressure at this 2 feet level. You will also get the same value of earth pressure, which is 2395 psf. Because since the Ka2 and Kp2 values are both same for this layer, so the gamma H portion of this layer and gamma H portion of this layer will be the same, and the plus this will the plus minus sign will make this equals to 0. So this value will be constant up to this point. And since we are solving the problem in conventional method, we have determined the value of the earth pressure in the base of the sheet pile, which is P4 is equals to 4500 psf. So this value we have determined. For the simplification and convenience, I would like to write down the equation of P4, which we have used for determining the value of earth pressure at the base of the cantilever sheet pile. Okay. This was sigma V1, this was sigma V2, and this is sigma V3. Okay.